Yeah, thanks for the invitation. And I mean, I have sort of a grab bag of content, so feel free to jump in. Um, because yeah, if you see something interesting, I probably won't be there for too long, so feel free to jump in and ask any questions that you have. But also love to learn more about. I always find the process modeling. I had a conversation with Gemini yesterday about what exactly that is, and so I think I'd be kind of interested to see kind of how that thinking can be used for AI. So I have maybe like one comment on what process modeling would look like in the era of AI at the end, but would love some thoughts on that. So yeah, so a bit about my role. I think basically like we're doing climate modeling in NVIDIA so that people can use the GPUs. And I think there's actually kind of a nice overlap between NVIDIA's like profit motive and what the user using of compute in areas like climate modeling. So it's like part of my focus of my talk will be that climate models get better by using more compute, um, and that's good for NVIDIA too. So my role is basically to on the research side to help figure out what the best way to use the GPU is, and sometimes that may look like a new AI model. That's been sort of been my focus. It may sometimes look like porting existing codes to GPUs, but I'm definitely more on the AI side, and focusing on both speed and accuracy of the type of models that we're building. I kind of have a pretty broad range. I've worked on NVIDIA's been great. I've been able to work on so many things, across climate and the weather stack. So that's kind of, and also a bit of fun methods development. So just a bit of advertising for kind of the models that we've been putting out recently. So we have kind of a fairly nice stack of models, especially in the weather forecast area. So we have kind of this forecast net model we've been developing over the course of a few years, which is kind of like a global autoaggressive forecasting model for medium range. And then we have a regional modeling portfolio, one for forecast application, Stormcast, and then the downscaling model, Cordif, and then also a global cloud resolving climate model, or climate emulator, if you will, called Climate Model. I think a few months ago, we announced three new models, kind of more on the weather side of things. Um, so I think they're, something like especially Stormscope might be interesting for other applications too. So it's kind of Atlas is kind of like our most skillful medium range forecasting system. We have a data assimilation model, which I was really heavily involved in, and Stormscope, which this is Stormscope. So we think about representation of processes in AI models. Um, really, it's hard to move past the picture norm, and we are able to basically through generating a model that through building a model that actually generates visual channels as well as IR channels. It's like it really looks good. And if you kind of Google and look it up and look at videos of it, it really just like looks like the weather moving around. And so I think that even though this model is it's skillful for nowcasting. Basically, the orange curve is a sort of the simple way to do nowcasting today. Like what do you get if you open the radar app in your phone? And the blue curve is Stormscope. So it's skillful compared to kind of the naive ways of doing things, but and also to physics based systems like the HER shown in triangle. But really moving back to the picture norm, I mean, to me, like in terms of representation of processes, like this model is trained only off of observation streams from geostationary, and the fact that the video looks good to me means something about how it's representing processes, and I'll get a little bit into that. We've also, I think, had a really fruitful collaboration with the Allen Institute, especially kind of in the early phase of the development of their ACE climate emulator, which is built off of the Fourier Newell operators. And so I think this is kind of one of our activities in climate emulation, and I think that their main selling point for the ACE model is it's able to simulate era 5 like conditions at 1500 simulated days per day, which is pretty remarkable. And you can do that on one GPU and generate all the data you need for scientific analysis. And we're starting to see that with papers like Shuyi Chen had a nice talk at AGU where she looked at ACE versus neural GCM, MJO diagnostics, and then there's some intercomparison efforts going on. AI MIP is an activity to look for, comparing a few different AI emulators trained off of era 5. Yeah, and just kind of running through the plot, so it's like seems to do a pretty good job at representing there's a lot of curves here, but the yellow curves all overlap, which is what we want to see. Somewhere in there is the error 5 curve, which is the dashed line. And it seems that the ACE model is able to represent trends over the observed record, including in its validation period, that it wasn't trained on, which is good. And then on the right is showing kind of more the classic hurricane diagnostics, and it seems like the model kind of overdoes the number of hurricanes per year, but the pattern is which is kind of interesting. Um, but the pattern is pretty good, and it seems like it's basically producing hurricanes in the right location. You can really see that just by looking at a video of the output too. It's like, okay, that thing is generating hurricanes. Um, so so that's kind of, I think, like really exciting model to use for climate applications. And I think even current climate sampling is an interesting area that people haven't really fully explored. So I would say this is a really high fidelity emulator of the current climate. Moving towards higher resolution, we've been building this climate in a bottle project, which is focused on sort of end-to-end synthesis of 5-kilometer global atmospheric states. We kind of started this project bottom up, and we had a cool like GSRM data set, and we decided what type of model should we train on it, and we trained this one. And so the basic idea is like we can essentially do generate 5-kilometer global states on a single desktop GPU. So it's sort of like a flavor of global cloud resolving modeling. It can be done on a desktop rather than a huge supercomputer. So these are just some snapshots of the generated fields. Again, the picture norm looks okay. It seems like it's looking like it's making clouds. I would say it's not as coherent as I'd like for things like tropical cyclones, but it's still pretty impressive. And you can see that, it's generating a OLR field, which is consistent with this vortex that you see in the wind field. So how do these models all work? They essentially have two key components to them in the ML framework. The first is computer power, and the second is data. And so the rest of the talk will kind of focus on those two important kind of raw resources. I had a session with Gemini. I was trying to make it produce like a funny steampunk diagram of like compute and data going together and producing an Earth system model. I wasn't super happy with the outcome, so I didn't include that slide. But I'll first dive into the compute story. And I think it's really important context here is this idea of scaling laws, which is really kind of synonymous with this idea that we can brute force problems by adding more compute. And we see this in Earth system modeling with this push towards higher resolution global cloud resolving models. So I think kind of one of the efforts that I've been tracking most closely is this NextGEMS project and subsequent work by Max Planck on the ICON model. And it's really about pushing these high resolution models towards faster throughput. So here they're saying that they're getting about 100 simulated days per day. And I forget what system this is performed on for two different global cloud resolving models running around 5-kilometer resolution. And subsequently, I think the kind of the state of the art is around 1 simulated year per day on all of Frontier, the DOE system. And so it's sort of like the whole supercomputer, you can get about a simulated year per day. And then these efforts are kind of advancing in parallel. And I think, obviously there's a lot of debate in the field about to what extent resolution helps, but this is one aspect of which I think is aligned with NVIDIA, is this idea that we can just add more compute, do more resolution, get a faster simulation, do more ensemble members, get more uncertainty. And so that's kind of I think the push of traditional climate modeling, which we're pretty aligned with. This idea of adding more compute and the model gets better is obviously true for all kinds of machine learning models too. So one nice example of this is if we look at an image generation context. This is using diffusion models, and we can see that the least compute is the upper left corner of this plot. And so if we make the model, we can use more computer power either by making the model bigger or by increasing sort of the resolution of the model internally by decreasing the patch size. And the amount of compute is essentially proportional, given proportional to this quantity here. we can see that the lower right looks a lot more like a dog than the upper left. Um, and you can find metrics for this too, but it's a pretty ubiquitous feature of AI models that the more compute you give them, the better they do, even with the same training data. We also see this in computer graphics. I mean, obviously, like if you can get more realistic looking computer graphics if you use a more kind of, this is not an AI model, but if you're using a more computationally intensive ray tracing approach, which is actually tracking individual rays of light, produces a more realistic looking image than sort of texture based approaches on the left. We also see that applying more compute on the x-axis improves LLMs, and this is why the NVIDIA is doing so well at the moment, because it seems like the more computer power you add, the more the more intelligence or the more accurate the models actually get, and that accuracy is not just on the task they're trained on, but also on other tasks. And so the one interesting aspect of this for AI systems, as opposed to physics-based systems, is that the computer power can be invested in a variety of places. So it can be invested in the training phase, which doesn't really exist in traditional modeling approaches. There's not really like a training phase for a model. And so we can choose to put a lot of computer power into the training phase. With LLMs, this idea of post-training, which essentially means tuning, which is kind of currently where a lot of computer power is put in climate modeling. But there's also this idea, and then there's the inference phase, which is like how much computer power you put into inference. So I'd say that with traditional climate models, there's like a post-training tuning, and then there's the inference, which is the simulation. But the nice thing about AI models is they can also invest into the pre-training phase. So it's kind of like they have more options about where to put your compute in a way that's optimal for your modeling task on a super high level. And we also see, I mentioned some AI models, but obviously like physics models, I would say they get better the more resolution you put in them. I mean, yeah, they're subject to tuning if they're still parameterized processes in global cloud resolving models, no question. But the picture looks a lot prettier, and I think that Bjorn Stevens had a recent paper about he's not calling it modeling anymore; he's calling it simulation, which I'm not sure I fully understand that distinction, but I do really like this. I think these models are beautiful. So how does the compute actually happen? So now I'm going to go into probably unfamiliar territory with how the hardware works. And so this is kind of a zoom in on the Volta generation, so 5 years ago generation of the GPU. And essentially, the two things I want to highlight here is there's all these parallel units that do computation called the streaming multiprocessors. But one of the most important things in this diagram is actually this HBM, that's high bandwidth memory. So that's where the data is. And so we've all like worked with data sets and had to like run computations on them. The same problem happens in the GPU. You have some data and you have to run a computation on it. And you somehow have to move the data from the computation from the memory where it's stored to the place where the compute is happening. So we see this all the time with I'm downloading data from ESGF, and I can't make my plots yet. This is the exact same problem, but just kind of in a smaller scale and at a faster for computation on the GPU. And so if we actually zoom in further onto like what each of those streaming multiprocessors is doing, we can see that it's devoted on the right to a variety of kind of integer floating point operations at double and single precision. But then there's something called the tensor core. And the tensor core is a matrix multiplication machine. And this is where a huge amount of the speed up of the GPU architecture comes from, is from this ability to do extremely fast, low precision matrix multiplications. So I think that's kind of worth noting. Like you can kind of look at like what percent of this is not actually on silicon. This is not like area. It's not to scale, but you can look at like generally speaking, a large amount of the resources that are being spent in engineering the chips is being put into this thing which does low precision matrix multiplications, which is not really used by physics-based models. I'll get into that. So essentially, like with any computation on data, it's essentially a race to get the data as quickly as possible onto the place where the computing is happening and send it back. And so there's this idea that's really important of the arithmetic intensity of a given algorithm, which is the number of operations that's performed per unit of information loaded. And this can happen. This is denoted as flops to bytes ratio. And there's two regimes here. First is memory bound. This is when you're where you're not doing where the data is bigger than the compute that can happen, and essentially you're bound on moving data from point A to point B through that memory bandwidth, sort of like slow network connection, if you will. And then there's compute bound, which is, hey, like the data is small, but the compute is really big, and I can do a ton of, and so I'm more limited by the actual tensor core, the ability to do the math. And if we look at some examples, addition is a memory bound operation. So we just load two pieces, we load A and B, we add them together. So that's two pieces of data loaded and one addition. So this means that this algorithm is limited by the memory bandwidth of the card, not the actual like ability for it to do computation. Same thing with matrix vector multiplication. You really have to do something more intense, like matrix multiplications, to actually get something that is using the GPU fully. And so the reason is every piece of data that you load for matrix multiplication has n computations done on it. Like I don't know if anybody ever had to do matrix multiplication in like an undergrad linear algebra class or something, where they like actually make you do it all. And that's great for the GPU. It's terrible for people, but it's great for the GPU. And essentially on the latest architecture, in terms of numbers, on the latest architecture, Rubin, if we look at the actual design of the card in terms of memory bandwidth and the total throughput of flops, essentially the break-even number is 181. So you have to do, matrix have to be at least 181 by 181 to fully leverage the card. And the problem with that for physical models is they leave a lot of flops on the table. They still benefit from the memory bandwidth of the card, that ability to move data from point A to B really quickly, but they do not benefit as much from the ability to actually do computations. And so AI models by comparison tend to be compute or nearly compute bound, at least certain parts of them. That's because they're based on a lot of dense matrix multiplication. So here I'm showing this famous component of the transformer model called the dot product attention, and it's just loaded with matrix multiplications. And these things are completely using the card. They're using every flop available. On the other hand, scientific computing looks like this. Here's like a Poisson equation stencil, loading three pieces of data and adding them together. Same thing with the Runge kind of type method. You can take any numerical method and it will typically have a sparse structure and look something like this. So this basically the main thing I'm trying to say is traditional modeling tends to be memory bandwidth bound and is therefore leaving a lot of flops on the table. And those flops are useful for making good models. And so I think this is kind of a really high level argument for why one might prefer an AI approach based off of things that run well on the card. Not to say physics models don't benefit from the memory bandwidth. I mean, that's the reason why physics models has a ton of memory bandwidth, but they're still leaving flops on the table. So I talked about compute. The next raw ingredient is data. And there's this kind of question. It's like, how does this even work? It's crazy. I mean, it seemed like really small data sets for 14,000 samples is not really enough to be training. Most people would not think that's enough data to be training a really large deep learning model from. And I have a few kind of hand-wavy explanations for why this might be. The first is that chaos is easy for ML. Everybody thinks of chaos as a hard problem. It's not. The chaos is easy because it essentially really well samples its own neighborhood. So if we look at like Lorentz 63, it is kind of fuzzy. Like it sort of densely samples the space around its own attractor, and it has this kind of fractal dimension or ergodic properties. I'm kind of throwing out big words, but essentially these type of dynamics are very good at creating training data sets. And that's why one reason why I think this has actually worked, especially for weather problems where this really chaotic system is dominating the the dynamics and making it really like it sees there's storms, it sees enough storms to essentially know how storms work. Another idea is this concept of kind of spatial locality. So we look at one snapshot of the Earth. It's not just one sample, right? There's many, like here's showing an image. Like there's obviously many images in this image, and so it's not really fair to consider a single snapshot of the planet to be a single sample of data. So, for example, we can think, in this snapshot alone, I think there's at least two hurricanes. There are, I counted them up. I think there's like a couple, like maybe a dozen or two synoptic scale eddies, and then there's obviously thousands of individual like thunderstorm clouds. And you can also kind of back of the envelope how many independent samples are for a given scale of interest, such as the synoptic scale, by doing kind of a simple, kind of uh, how many synoptic scales are there in the planet. Turns out like there's around 500, 1,000 by 1,000 kilometers in in a single snapshot, 14,000 days, and that ends up giving you a 7 million independent sample training data set, which is starting to be pretty reasonable compared to something like ImageNet, which is sort of the famous image classification data set that has about 1 million samples. So anyway, spatial locality, it's not just one image, it's many things. It's a ton of data in each realization of our each observation. So that was the good. I think the bad is sometimes we run into these limits of data limitations, and I'll first go into duration. So there's this fact that autoregressive models tend to overfit on slow processes. So this is showing the validation versus training loss in the stratospheric temperature field of ACE. And we can see that when you only give it 10 years of data, it shows very big overfitting. The validation curve is much worse than the training curve. We don't see that overfitting lower down in the atmosphere, I think, because it's a faster timescale part of the dynamics. But when we add 100 years of data, it seems like the overfitting goes away. So I think that's pretty interesting. We see that also for the ocean. Ocean's slow, and so there's a kind of a cool, I think maybe one of the most exciting coupled model efforts in AI is the Samudra ACE paper. We can see that the atmosphere component doesn't overfit, but the ocean does. And the sort of impact of this overfitting is that it seems to underestimate long-term variability. And so the physics model here that Samudra was trained on is shown as black, has a ton of power at the, above the El Nino timescale. Whereas Samudra ACE is really like, it gets El Nino, but it doesn't get anything slower than that. And so I think this is really highlighting the limitation of the length of the data that you need. So if you have a specific process in mind, you do need a data set that has many independent realizations of that process. This is kind of the main rule of thumb. You might need a lot of ocean data to actually train a model like this. The other limitation is kind of the correlate, another corollary to this idea is resolution. So there's been a lot of talk about like how long of a time step can AI take, and I think that there's this interesting idea that I think hasn't been quite realized, is that the length of the time step that an AI model can take is proportional to the amount of blurring that happens. There's this connection between time and space. So it's low resolution in time equals low resolution in space, and you can see that by doing kind of a scale dependence of the predictability. And there's a really nice kind of literature out there in the convection resolving world for this. And you can make curves like this, which is the scale at which everything below the black line, the scale at which the maximum scale predictable at a given lead time. So for 6 hours, it turns out everything below 70 kilometers is unpredictable, gets blurred away. And then so that's kind of interesting, because we often see with these quarter degree trained error 5 models at 6 hours that they blur out to 1 to 100 kilometers right away. The effective resolution is 100 kilometers, and that limitation is coming from the time frequency at which they're trained. Now, if we kind of extrapolate this curve down to convective scale, it turns out that you need around 10-minute resolution for a kilometer scale. And there's not a lot of data sets out there that are 10 kilometer that have 10-minute resolution at those scales. One of those data sets is like geostationary satellite is one of those data sets. But if we look at reanalysis-based data sets, they typically have hourly resolution, just inadequate for representing this process. And for that reason, for hourly models, they need to have this kind of diffusion approach stacked on top to sort of add the variability that's not being explicitly resolved. Whereas for a 10-minute trained autoregressive emulator, we actually do see it generate its own convective systems by explicitly resolving the process at hand. So yeah, just to conclude, I maybe covered more ground than I should have in this talk, but I'm pretty excited about AI models mostly because they use the GPU and they're fast. Um, and this kind of implicit is this hypothesis that more compute makes the model more realistic, um, and and also there's this interesting idea that you can put that compute into three different phases as opposed to just tuning and inference. You can also do the pre-training phase. Um, so we see that with ACE, right? I mean, it's like you can. So Era 5 took a long time to make, but you pre-train on ACE, you make this. You put a lot of compute into the training, but then the inference is very cheap. The I think where to go with data, and the way I think about process modeling is really in designing the training data to match the physical process of interest. Um, and so everybody's been lucky with Era 5. I mean, it's just basically you could tell AI to train an AI model on it and it would do fine. Because it's the perfect data set for the synoptic scale weather. 6 hourly, 1 degree-ish resolution. It's just perfect for that task. Convection requires finer resolution and time, and slower processes require longer data sets. And these are kind of, I think, more difficult challenges to solve, and where things like physical models and process modeling come in. So note today I haven't discussed like models being more accurate by ML being better method. Um, I haven't discussed like structural errors or things like that, but mostly just focusing on the compute and the data.
Hi, Noah, this is Kara Lamb. I'm at Leap. I guess had one question. Like your scaling laws, you're sort of assuming I mean, these are purely data-driven models. Have you thought how this might change if you included like some physical physics in the models, like something like neural GCM, or do you think that would like change the picture in some way? Or do you think that's like a useful approach?
I think I was trying to be like high level with that. So the scaling laws I showed specifically were for LLMs and diffusion transformers. Um,
Right.
I think that it hasn't really cleanly been done for a lot of the AI model, for a lot of the physics based, or sorry, for in this domain. Um, I think that if we look at the scaling laws literature, it's very nice because everybody's using transformers, so it makes it pretty easy to understand in a lot of other domains like image and whereas like in the weather domain there's so many architectures, and there was a recent like scaling law paper. They didn't look at neural GCM, but they looked at like GraphCast and SFNO and a few different AI models. I forget, it's out of Torsten Heffler's group at AETH. And I feel like that paper was just
Mhm.
like, it was just hard because there's so many architectures. It was not as comparable as we would expect. It's hard to pull like a clean scaling law out of it when you have like 10 different ways, 10 different fundamentally ways of doing it. Um, but still, I would expect that, yeah, more flops would result in a better model. And at least and to comment on physics-based models, I think that's kind of implicit in just like more resolution leads to more accuracy. So I think that that's sort of at least implicit in a lot of physical modeling too.
Right, go ahead, Eric.
Yeah, thanks, Noah. This is really interesting. One thing that I think will always be with us is physical models. And the problem you have with physical models is, at least, I'm at the National Science Foundation, we don't have enough money to sort of drive technology. So we tend to use whatever architectures are being developed for the sort of commercial sector. And, everything you say is kind of right. I mean, certainly you look at these Poisson sort of stencils and things like that, and it's all addition. That doesn't mean you couldn't do things differently. that there is no representation of Navier-Stokes that's better suited to sort of matrix-matrix multiplication. And I'm just kind of wondering, are people working on different ways of doing the physical modeling that are a better match for, the GPU hardwares and things like that?
Yeah, I mean, I think like spectral methods tend to do more matrix multiplications. There are sort of more computationally intensive, like higher order methods generally. Well, I think, yeah, I haven't, I'm not like the full expert on this. Like, I'm sure there are some papers trying to use like the tensor core for that. The other comment I would make about this is like, obviously we're still like Error 5 is basically the output of a physical model with some data with data mixed in. And so really like this overall, I would say is just like we could do the physical model as like training data generation. So we're still doing physics. We're just like the inference doesn't have to be the physics model. We could just have it be part of like the earliest step of the whole modeling stack is like the generation of training data sets, and I think that's roughly why AI has been so successful in this domain. It's kind of that's what we're doing.
I guess, I mean, that gets into another question, which is, it's fine if you're trying to sort of, I guess, emulate, predict, forecast, the observed world. But, in a lot of the research that, my program funds, we'd be looking at kind of questions of, how will, intensity of rainfall change if you add carbon dioxide, if you change the aerosol emission sources around the globe, things like that. So it's, I guess it gets a little tricky when, you're really trying to sort of go off the sort of lookup table of any training that you could do on reanalysis data sets and things like that. But again, I don't disagree. I think that's a whole nother conversation to have, the way people are adopting AI2 and other models to do these more sort of, theoretical climate kinds of questions.
I think it's like the lookup table point is well taken, but if that lookup table is like, what does a storm look like if the temperature is slightly warmer, then that lookup table can be like, oh, I'm going to look at what Indonesia looks at instead of looking at like what 20 years from now looks like. So the lookup table, if there's a lot of locality there, the lookup table is, there could be a lot of things in that lookup table, a lot of data to constrain it. And I think that's been something interesting with AI models is just that there is a lot of data even in something like Era 5 that's relevant to climate change. But yeah, I think it's definitely like being able to quantify that how much data is needed in order to do a certain task is the way to do it. So for example, like for the climate model project, for that super resolution component, only needed 4 weeks of data from the cloud resolving run. Made no difference to have 100 times more than that. So, and that's because each snapshot is a lot of data. Sometimes like the terabytes on disk is not necessarily a bad proxy for how much data it is.
Yeah, that's a good point.
All right, go ahead, Alex.
Thanks, Noah. That was interesting. I have a dumb question and then a follow-up question from what Eric asked, and I guess I'll ask the first one just to follow up. I guess, I maybe I'm misunderstanding, but like, for example, low cloud feedbacks and climate models and the current data we have, we could reach an equilibrium that's not in the data set, in like the historical record, unless we went to, paleoclimate timescales or something like that. And so I wonder, like, if that regime, say, of your training data set, Era 5, still isn't getting, it can't get that sort of prediction and have a realistic output if you don't have the training data that supports it.
Yeah, I mean, it's like you go to the hardest aspect of of climate modeling, but
yeah.
I mean, if I had a global LES and I had an emulator for it, would you believe it?
Say it again, LES, you said?
If say I had a global 200 meter model that ran reasonably quickly, would you trust that?
Depends on, I guess, a lot of things. It's just the scale of, I don't know. Yeah, possibly.
But I guess the point is you would know how to interrogate it, right? You have the right sort of, pieces in the model that you can sort of map it onto your physical ideas of how the system works. And so there's things you can do. I'm not saying you don't have things you can do in the AI world. I think people are inventing really clever strategies, but that whole question of how do I interrogate this thing seems to me to be key.
Yeah.
Yeah, I think we could build a global LAS emulator and maybe be able to run it. I think like I'm kind of in favor of explicit resolution of processes. But I agree something like ACE is sort of like learning an implicit parameterization, course grading, if you will. And I think something explicitly resolving, I think, is an interesting direction to go. And it's good for AI because brute forcing is sort of what the card wants to do.
Yeah. My stupid question was, you were saying something about error 5's nominal resolution is, what did you say, 1 degree, just because of the time resolution. I guess, does that have to do with the data assimilation? I guess I didn't understand that because, yeah, it's hourly data is the output, but I assume that's not in sync with the DA.
That statement was related to models trained with quarter degree data to make a 6-hourly time step. Their resolution is 100 kilometers. So that's the statement there. So if you train a model to take it doesn't matter. You could train it with 1 kilometer data, give you almost the same answer. Or 100 kilometer data, it gives you the same answer as training with 25 kilometer because that time, you're not really resolving in time the stuff below. That was that statement. That said, error 5 is a funny data set. It's trained, has a 12-hour data assimilation window. So essentially within each 12-hour increment, it's a free run of IFS. But it's optimized to match observations over that whole window. So it's like, is the hour? I would say like, is the resolution of error 5 12 hours, or is it? Yeah, so that's definitely a bit of a tricky.
Well, the convective parameterization and a lot of the microphysics or the like cloud processes and moisture are all prognostic and aren't really driven so much by the data assimilation at sub 12-hourly timescales. Yeah,
so if it's sort of not really being that adjusted by the observations, then yeah, it does seem like you're sort of trusting IFS's representation of those processes. If you're sort of more on like that synoptic scale time scale, maybe it's more data than model. But yeah, so maybe it's high resolution, but it's basically model output. Might as well work with the free run of IFS rather than error 5. Yeah.
Okay, sorry for the hard questions, but
No, these are
just
good
wanted a
questions,
clarification there. I mean, I feel like, yeah, error 5 is doing some great things though with like their parameterizations too. So I feel like free running IFS is also something that's much better than the setup of many other reanalyses. And it shows in how they represent clouds. And obviously they're, not perfect compared to observations, but if there's something we can learn there, would be good. And also they use the spectral, they're the spectral, what am I trying to say? The way that they run their model, spherical harmonics, using spherical harmonics. I wonder if that's any more efficient for this, taking advantage of GPUs.
Yeah, I didn't mean to say error 5 is not good for sub-hour. I haven't sub 6 hour. Just the models all trained. None of them are actually explicitly resolving the sub 6 hour stuff. That's all I was trying to say. Yeah.
All right, Juliana, I saw you put your hand down. Do you still have a question?
I was concerned about timing. Do we have time? Or should we move on?
Do you think it's relatively quick? I think we can sneak it in if it's quick.
It was a more general question. I can ask Noah on email.
Okay, and then in that case, I'll go ahead and ask Liz, is your question relatively quick?
Yeah, I think this is relatively quick. So kind of following off the discussion. So when we think about if a climate model is doing really well, if we want to really interrogate it, sometimes what we have to do is go into the process level, like a process level diagnostic. And so my question is is the model getting the answer right for the right reason or wrong reasons? And so I'm just really curious, are the architectures, the models that are coming out today, are they really set up for the kind of diagnosis that would allow us to look into that? Like, do they have, like, what are there sufficient variables that you could interrogate models in these ways? Are people thinking about how one might try to go after that more kind of intense evaluation, or is that still ahead of us?
Do you mean like some sort of like MSE or MSE diagnostic or
Beyond beyond that, yeah. So like, or not like us, not just mean squared errors, but yeah, going into moist static energy if we're talking to MSEs.
Yeah, that's the MSE I meant. Sorry, yeah, overloading. Yeah, so I mean, ACE has a moist static energy conservation. I think the problem with the AI world is that, you know, a lot of these diagnostics that we have, you know, they're pretty low dimensional. The model can still cheat around them. You know, it can still have good. So that's kind of, and we see that with, you know, physics-based models too, right? I mean, you know, compensating errors, adjusting to, you know, they'll kind of work their way around their conservation laws and, you know, the things that can actually constrain them to, you know, produce a good match against observations. But yeah, so I think that maybe the models do need more guardrails. There's definitely like kind of less, like, you know, you're not gonna be like, oh, like in the microphysics I, you know, had the wrong rain rate or something. Like there's not gonna, that sort of low hanging fruit's less available. But a lot of those physical modeling, I think, can go into the creation of training data set. You know, so obviously if we think, you know, we don't have direct observations of ACI or, you know, something like that, but we do trust LES, you know, that we could like kind of put the tuning onto the training data or generation side and the process. That's sort of, maybe, I don't know if that answers your question, but
I think it gets there. Thanks.
yeah. Less on the modeling, basically more in other parts of the process than the actual like core modeling effort. But I think that what the AI just generally takes less moves. The actual building of the model is not really that hard. It's more about like, yeah, it's way less work than GCMs. It's just like, you know, it's a few hundred lines of code.